In our observations of a string, we had a 20-meter string under a tension that we call T. Okay, this is a tension that was created by stretching out one rubber band to a known length. Let's see, these papers are about to fall. I'm going to just manipulate these a little bit so nothing too tragic happens here. Hopefully that'll keep things under a little better control. Okay, sorry for the interruption. Okay, we noted, we had the tension T from one rubber band. 1.47 meters of the string had a mass of 0.0095 kilograms. Is going to be relevant in a minute to what we observe. Okay, now these are the observations that you've already made or are going to make in your experiment. Now your numbers might be a little different. You might not have the same string that I did, but in any case, this is your situation. This represents a pendulum that we used. We just let a short pendulum, actually using the pendulum stand, just oscillate back and forth, and we timed the pulses down and back with the oscillation of the pendulum. We could see several pulses go down and back, 5 or 6 pulses under this tension, and by releasing the pendulum at the same instant we plucked the string, we could then watch the string and the pendulum and see that the pulse came back in the string at the same time the pendulum came back to its original point. Every time the pendulum came back, the string came back, or the pulse came back. Of course, we had to adjust the length of the pendulum to do that. Okay, the delta T, the time required for the round trip, will be in the same proportion to the tension in the string as the reciprocal of the pendulum length. Now, that's not a real profound statement. The reciprocal of the pendulum length, let's back up a second. That is a profound statement because we observed that. We observed that the delta T for the round trip was in the same proportion to the tension as the reciprocal of the pendulum length. And that's a real significant proportionality, as we'll see. Now, the actual numbers we got, the tensions were about 5, 10, and 20 newtons for 1, 2, and 4 rubber bands. The L lengths of the pendulum, not the string, were 64, 32, and 16 centimeters. So that we see that as we double the tension, we have the length of the pendulum. That happens both here and here. And these are good, honest estimates, okay? Within a centimeter or so, these are correct. Now, we didn't go to pains to observe L with great accuracy. We actually, in the experiment, didn't bother taking the pendulum stand with us. We just kind of held the pendulum and then measured it. In any case, these are the results we got. Your results will be even more precise, and you'll probably find a similar proportionality. Now, the delta T that we get here, the time interval between pulse returns, corresponds to the length of the pendulum. Remember that the delta T, the period of the pendulum, is 2 pi over its angular frequency omega. Basic principle, simple harmonic motion, angular frequency is equal to the square root of k over m, the restoring constant over the mass. And for a pendulum, without going into the details, that's going to be the square root of g over L. So that we have 2 pi over the square root of g over L, g being the acceleration of gravity. Plugging that in the lengths, we easily determine these delta T's. Now, from these delta T's and from the 20-meter length of the string, we determine what the velocities are. And we see that the velocity under a 5 Newton tension is 25 meters per second. Under 10 it's 36, under 20 it's 50 meters per second. We note that the velocity appears to double between here and here. As we quadruple the tension, we double the velocity. And we like to refer to quadrupling as fourpling. So if we fourple the tension, we double the velocity. This is an indication that the velocity is in some way possibly proportional to the square root of the tension. It turns out that the equation given in your book, and we derived this for the university physics students using the impulse momentum theorem. It's not a real difficult derivation. But on the university student's disk we do have a derivation of this. The velocity of a pulse in a string ought to be square root of T over mu. Square root of tension divided by the mass per unit length. Mu is the mass of the string divided by its length. Now this L is not the length of the pendulum. We could get into a little confusion there. I used L for the length of the string and for the length of the pendulum. In any case, this is a mass per unit length that we observed and was indicated on the original figure. So that our tension was 5, 10, and 20 newtons. The observed velocities are 25, 36, and 50 meters per second. The velocities, which would be the square root of T over mu, using the square root of T over mu for the approximate tensions that we observed, should have been 28, 39.5, and 56 meters per second. Now the observed velocities were a little bit less than the ideal velocities, and there's some reasons for that. One reason is that the rubber band kind of loses its tension as it stands there, as it sits there, stretching the string. So the tension in the rubber band isn't always the same, so that the actual tension might have been just a little bit less than what we estimated here. The rubber band idea is good because the rubber bands are accessible and easy to use. It's not so good because rubber bands don't maintain their tension real well. Another thing is that the string sags from one end to another. And that means that the tension in the middle of the string is a little bit less than on the ends, which would imply that the velocity in the middle is a little bit less than the velocity in the ends. So that the observed velocities we might expect would be less than what we get when we do this calculation. Nevertheless, these are pretty close. This is accurate usually to within about 10 to 15%, and those are pretty good results. They kind of validate what our theory tells us.